In 2019, I began my van life road journey. I soon realized that having a stable power system is crucial for long-term living in a vehicle. I opted for an all-electric setup, but frequently ran into power instability issues when using an inverter. The bulky batteries also made charging a hassle. That got me thinking, what kind of energy storage system is truly suitable for long-distance travel? After 2 years of testing and adjustments, I eventually adopted a 24-volt DC system, completely eliminating the inverter and instead using an MPPT controller paired with rooftop solar panels. This not only simplified the system and made the battery lighter, but also significantly reduced energy loss. With continued real-world use, I improved the BMS and added an active balancing function to maximize battery capacity and create a more durable and stable off-grid power system for van life. When I shared my real-world testing experiences online, many people expressed in this DC-based setup. To help those who resonate with my design philosophy access a 24-volt DC power system, I decided to launch it on Kickstarter. My hope is to help others with similar needs build their own power systems more easily and reduce the time lost on trial and error. Next, I'd like to introduce the core design philosophy and structural setup of the entire system. In fact, parts of this content have already been briefly covered in previous videos. If you're interested in the technical details, you can find more in-depth information by checking those earlier videos. The system is composed of several key components. 1. Cell configuration. At the beginning of my van life, I used lithium-ion batteries to power my setup. However, keeping lithium-ion batteries in a vehicle for extended periods always raised safety concerns for me. That's why I decided to switch to lithium iron phosphate batteries as the main power source. These batteries have low internal resistance, which means they remain cool during charge and discharge cycles, providing excellent discharge performance. In addition, they can withstand over 2000 charge cycles while maintaining up to 95% depth of discharge. Lead acid or lithium-ion batteries, they offer a lifespan of up to 20 years. More importantly, they don't contain flammable materials like some lithium-ion batteries do, reducing the risk of explosion. This makes them a much safer option. These characteristics make LiFePO batteries especially suitable for long-term use, and they became the obvious choice for this system's design. 2. System voltage. Choosing the right system voltage is a critical decision. Or 72-volt systems offer better performance and compatibility with AC appliances and help reduce transmission losses. They also require more battery cells in series, which increases system complexity and cost. So in practice, they're not always the best option. On the other hand, 12-volt systems are extremely common in automotive applications, but when the power demand is high, the required current increases significantly. For example, to supply 200 watt of power at 12 volt, the current would reach 16.7 ampere. Such high current leads to substantial voltage drop along the wires and imposes strict demands on wire thickness and heat resistance. If the circuit is overloaded or overheated, it can pose serious safety risks. A 24-volt system under the same power load cuts the current in half compared to 12-volt, greatly reducing voltage drop and heat buildup, improving overall stability and efficiency. Furthermore, 24-volt systems are commonly used in trucks and commercial vehicles, so standard 24-volt appliances and accessories are widely available and easy to source. Considering both performance and safety, 24-volt emerges as a well-balanced voltage choice for the system. It also offers excellent expandability and compatibility, suited for various van life power needs. 3. Modular circuit design. The entire battery power system is made up of several modules: the BMS and battery protection and overall management. An MPPT controller optimizes charging efficiency and power flow. A main control board manages power calculation and display. All other modules are integrated to simplify wiring complexity. The modular design allows each part to be independently tested and replaced, making future maintenance and upgrades easier. It also streamlines the circuit layout by minimizing unnecessary connections and reducing overall system complexity. I also selected high-quality, industry-recognized components to ensure performance and reliability. 4. Eliminating the inverter. Initially, I used a 60-volt lithium-ion battery with an inverter to power appliances in the van. In theory, this allowed household appliances to operate as usual inside the vehicle. But in practice, it caused many headaches, especially when using high-power devices. Even if the battery still had enough charge, the inverter often couldn't sustain the output, causing appliances to shut down unexpectedly. This severely impacted the overall user experience. Inverters also produce noticeable fan noise when operating, which becomes especially annoying at night or in quiet environments, disturbing rest and peace inside the van. Worse still, inverters generate significant heat and require extra space for cooling. And converting DC to AC involves energy loss, typically with an efficiency of only 85–90%, meaning 10–15% of the energy is lost during conversion. That's why I chose to eliminate the inverter altogether and design a pure DC-powered system. This not only removes noise and cooling issues but also avoids conversion losses, allowing the battery to directly power DC appliances with greater efficiency and longer runtime. While most people bring household appliances into their vehicles, this approach increases the burden of transport and requires extra thought for securing and storing them. By contrast, appliances designed specifically for van life and DC use are more compact and lightweight, integrating better with vehicle interiors and enhancing usability. You can also choose DC appliances with various power levels and functions based on your specific needs without being limited by inverter performance. Overall, eliminating the inverter significantly improves efficiency, stability, and quiet operation while reducing potential equipment failures and wasted energy. 5. Structure and heat dissipation. Since there's no inverter, the overall design does not require fan-based cooling. Instead, the battery and circuit modules simply need adequate space for passive heat dissipation, ensuring effective thermal conduction. These components are enclosed in a sturdy casing which is built with materials and structure that resist punctures and impacts. The battery housing was specifically designed with vehicle camping in mind, striking a balance between safety and durability to ensure long-term reliability. 6. Charging considerations. In designing the vehicle power system, I intentionally chose not to include vehicle charging. This decision was made after careful evaluation. While many people use their vehicle's alternator to charge their onboard batteries, this approach introduces several practical issues and risks. Vehicle alternators are primarily designed to power in-car electronics and to recharge the starter battery. Using them to charge a large external battery bank can overload the alternator, potentially affecting the stability of the vehicle's electrical system and even damaging the alternator itself. So, I opted for a more reliable and stable charging method. A dedicated solar charging controller was integrated, optimized for use with lithium iron phosphate batteries, making the charging process both stable and efficient. Solar charging offers a continuous and clean energy source, especially suitable for long-term parking or camping where ongoing power supply is needed. Additionally, when rapid charging is required, I use a dedicated AC/DC charger powered by shore power or a generator. These two charging methods are far more flexible and efficient than alternator charging, and they significantly reduce dependency on the vehicle's electrical system. 7. User interface. The top of the battery features three 24-volt 10A cigarette lighter sockets, each capable of delivering up to 240 watts of output power. Each socket is equipped with an individual 10A fuse to ensure circuit safety. A 15A high current terminal is provided to support larger power demands. To enhance long-term reliability, I chose aviation for both 24-volt output and charging input. For extended outdoor use, a dedicated 24-volt solar input port. I specifically designed an MC4 to GX12 adapter cable to connect directly to the system. To accommodate small, low-power devices, a 12-volt output is also available, preventing unnecessary energy waste from using high-power ports for small tasks. To meet the needs of mobile charging and small appliance use, I included 4 USB ports capable of fast charging smartphones, tablets, cameras, and other mobile devices. As for the Type-C port, because of its fragile internal structure and high risk of damage from frequent plugging and unplugging, I intentionally chose not to include it directly. Instead, I recommend using a cigarette lighter to Type-C adapter for greater flexibility. If it breaks, it can be instantly replaced, and users can choose adapters with the right specs for their devices. This approach reduces the risk of port damage and ensures compatibility with the constantly evolving PD fast charging standards. Pressing the display button activates a simple percentage-based battery level indicator, showing the remaining battery capacity directly as a percentage rather than through complex data or graphs. This allows any user to quickly understand the battery's status at a glance. To enhance both convenience and safety, I designed a master power switch, essentially the battery system's main power button. This button controls the power supply to all ports, ensuring the system can be completely shut off when not in use. With this interface setup, the system meets a wide range of van life power needs while remaining simple and intuitive to operate, allowing users to find the right power solution for any scenario. From material selection to final assembly, every step of this battery's construction has undergone rigorous inspection and testing, ensuring reliable performance even in unpredictable outdoor conditions. To achieve efficient and safe energy storage, I chose to source brand new lithium iron phosphate cells directly from EVE Energy. Each battery cell was individually tested for performance and consistency to ensure it was in optimal condition. Further enhanced safety, I applied insulation stickers to the surface of each cell and secured the battery pack with insulating tape. For high-efficiency energy transmission and operational stability, I use high-conductivity copper busbars with a cross-sectional area of 22.5 mm² to connect the cells in series, further boosting overall system efficiency and stability. Next, the battery pack was installed into a 1 mm thick stainless steel casing with insulating panels added to secure the battery assembly and prevent internal movement. At this stage, combining the BMS MPPT and mainboard was installed onto the battery pack. Then came the installation of the battery's control panel. First, I mounted the 24-volt solar input port to allow direct connection from solar panels to the system. Then a 12-volt DC jack was added for low-power appliances, followed by aviation connectors for 24-volt output and charging input. This is the battery's master power switch, which controls power to all output ports. Pressing this button powers the entire system on or off, enabling quick and convenient operation. A Hall effect Coulomb meter was also installed to accurately monitor current flow using Hall sensor technology, allowing the system to track energy usage continuously without affecting performance. Once internal assembly was complete, I ran an AC charging test alongside checks on all output interfaces to verify that every port was functioning properly. The top of the battery also features 3 24-volt Tampere cigarette lighter sockets, each capable of delivering up to 240 watts of power. External fuses were added to each of the 3 ports to enhance overall safety. Devices were then connected to the sockets one by one to confirm that power delivery was stable and reliable. Finally, I tidied up the wiring and secured the battery housing with its top cover. After this series of careful assembly and thorough testing, QPower battery system was complete. Despite its compact size, just 26 by 22 by 21.5 cm, it packs 2520 watt-hour of energy, achieving a density of 200 mAh per liter. QPower stands out with a clear advantage in volume, making it the most compact, high-capacity power storage solution currently on the market. To ensure that this battery, designed specifically for van life, would perform as expected in real-world use, I carried out extensive field testing and refinements. From initial trials to long-term durability evaluations, every aspect was thoroughly examined and optimized. This was not just to validate system stability, but to ensure optimal performance across a wide range of van life scenarios. During the initial testing phase, I used an electronic load tester to perform constant current and constant power discharges, verifying whether the voltage remained stable under varying loads. In real-world simulations, I connected the battery to multiple devices simultaneously, including an air conditioner, laptop rice cooker, fan, and LED light strips, mimicking high load usage conditions found in daily van life. The results showed stable power output from the battery, with the temperature of connectors and wiring remaining safely below 50 degrees C. Even when multiple devices were running at the same time, there were no signs of overheating or power instability, demonstrated the battery system's excellent heat dissipation and power management capabilities. However, after repeated charge and discharge cycles, I noticed a voltage imbalance developing between the 8 individual cells. Such voltage differences persist over time. They can shorten the battery's overall lifespan. In the original design, I used a passive balancing system, equalizes cell voltages by dissipating excess energy as heat, an approach with relatively low efficiency. After prolonged use or frequent cycling, the cells showed significant voltage deviations, impacting the system's overall performance. To address this issue at the root, I decided to implement an active balancing system. Active balancing uses charge transfer technology to efficiently move energy from higher voltage cells to lower voltage ones, ensuring that all cells stay within a safe and consistent voltage range. After upgrading the system, conducted long-duration use tests and repeated charge-discharge cycles. The results clearly showed that the active balancing system significantly improved charging and discharging efficiency and reduced voltage imbalance. After this full round of testing and improvements, I gained even greater confidence in this battery system, purpose-built for van life. It's now more stable, longer lasting, and better suited to meet the real-world demands of mobile off-grid living. In van life, the battery system plays a critical role, especially when there's no access to external power sources. How effectively you manage your battery directly impacts the overall quality and convenience of your daily life on the road. Lighting is one of the most basic necessities in a van environment. When night falls or campsite lighting is insufficient, both interior and exterior illumination becomes essential. To ensure long-lasting and energy-efficient lighting, LED lights are the go-to choice. These lights often charge directly via USB-A ports, requiring no inverter conversion. They offer high brightness with low energy consumption, and even after extended use, they stay cool to the touch. USB-powered light strips or small bulbs can also be connected directly to USB ports or cigarette lighter sockets, meeting both indoor and outdoor lighting needs. Modern van life also heavily relies on a range of electronic devices. Whether it's smartphones, tablets, laptops, or various photography gear, all require a stable power supply. To support these needs, the battery system includes multiple USB-A output ports, allowing for fast charging of several devices simultaneously and relieving the stress of battery anxiety. For higher powered devices like laptops, a cigarette lighter to Type-C adapter can be used to provide reliable charging. Food and cooking are also an integral part of van life. That's why I use a DC-powered refrigerator, specifically designed for mobile use, connected directly to the 24-volt cigarette lighter socket. When hot water is needed, I use a 2000 W DC electric kettle via the same socket, whether for making coffee or simple meals. It's quick and convenient, adding comfort and a home-like feel to outdoor living. I also use a 240 watt DC rice cooker for preparing meals and stews, again powered through the cigarette socket. For quick and powerful heating, I turn to a 700 watt DC induction cooker using an Anderson plug for stable output. Thanks to its even and rapid heating, offers much better safety and ease of use compared to gas stoves or portable burners. Although DC induction cookers have lower power than household units, they are more than sufficient for outdoor or van life scenarios. For connectivity, I've chosen the Starlink Mini as the core communication and internet solution for van life. The device not only provides a stable Wi-Fi connection but also supports multiple devices at once, greatly enhancing overall convenience. Powered through the 24-volt output, it operates reliably without issue. Through careful system planning and integration of a wide range of equipment, I've achieved a power management setup that's efficient, stable, and long-lasting in daily van life. This power system configuration has significantly elevated the overall quality of my mobile lifestyle. Ever since I began living on the road, unstable power supply has cast a constant shadow over my travels. The helpless feeling of losing electricity in the wilderness time and again made me ask myself, what if there were a power system that could truly solve these pain points? This is QPower, a battery born from real-life needs, refined through hands-on testing and continuous improvement. It's more than just a power source, it's the key tool that helped me redefine van life. Like most people starting out, I used open flames to cook, but I quickly realized the downsides: smoke, carbon monoxide risks, and potential fire hazards. In contrast, advantages of electricity are undeniable. Just plug in your device and everything runs quietly and reliably. This choice freed me from location constraints, eliminated dependence on campsite infrastructure, spared me the stress of constantly calculating power usage or making compromises. And for long-distance travel, one thing matters most: QPower is compact, quiet, and completely silent. That means you don't have to sacrifice sleeping comfort for battery space or give up your entire trunk to fit bulky equipment. There's no need to install cooling fans or reserve space for heat dissipation. It's not just a battery, it's a mobile power system that gives you the confidence to venture farther, live simpler, and stay safer. I've achieved my dream of true power freedom. Now, I want to share this battery with you. If you love van life but constantly struggle with power issues, QPower is the solution you've been searching for.